students. Now we shall look at some few numericals on ideal gas. So this is numerical 1. A tank of 0.34 meter cube contains H2S at 22 degrees centigrade, the hydrogen sulfide. When 2.3 kg of gases are drawn out, the temperature in the tank becomes 15 degrees centigrade and pressure is 10 bar. Find the mass of the gas in the tank initially and its initial pressure. So, what is given here? First is the tank volume, that is 0.34 meter cube. Then the gas is given, hydrogen sulfide. Then the temperature is given, initial temperature 22 degrees centigrade. So next what they are, 2.3 kgs of gas is drawn out. So the temperature falls to 15 degrees centigrade. And the pressure now is 10 bar. So what is the question asked is, initially what was the tank gas, mass of gas in the tank, and what was the pressure? Temperature was given as 22 degrees centigrade. Now molecular weight of hydrogen sulfide, H is 1, so H2 means 2, sulfur is 32. So you please you have to remember, and how you remember, I'll just simple, I'll tell you. Hydrogen is 1, H is 1, carbon C is 12, okay, nitrogen N is 14, oxygen O is 16, sulfur S is 32. This is how I have remembered. So in ascending order, you can also remember 1, 12, 14, 16, 32. So 1 is hydrogen, 2 is 12 is carbon, 14 is nitrogen, 16 is oxygen, and 32 is sulfur. So here H2 means 2 plus 32, that is 34. Now universal gas constant R bar, that is fixed as 8.3143 kilojoules per kg mole Kelvin. So now particular gas constant, now for hydrogen sulfur, when you have to find out, R is equal to R bar divided by M. So R bar is 8.3413 and M is 34. So dividing 8.3143 divided by 34, we get R, the gas constant, is 0.2445 kilojoules per kg mole Kelvin. Okay. Now mass of the gas left in the tank after 2.3 kg of gas is drawn. So M is equal to P2. We know that PV is equal to MRT. Okay. So PV is equal to MRT. Now we are now for condition 2. So rearranging this, what you get? M is equal to PV by RT. For condition 2, volume is same, R is same. So we are not writing V2 or R2. Okay. Only pressure was changed and temperature is changed. So we are written P2, T2. Volume and R is fixed in this case. So substituting values of P has told the 10 bar. 10 bar means 10 into 100, that becomes in kilopascals, into V, volume is 0.34 meter cube given, divided by R is 0.2445, we have calculated just now, and temperature T2 is 15 degrees centigrade. So 15 plus 273, that is 288 Kelvin. So we have to be very careful in this ideal gas equation. This temperature has to be always in Kelvin only. So mass M is equal to 1.83. So 4.83. So the original mass in the tank is 4.83 plus 2.3 which was drawn out, that was 7.13. Now again using the ideal gas relation for initial condition, that is condition 1, PV is equal to MRT. Okay, now we have to find out P here. P is equal to, for condition 1, M1 RT1 divided by V. Okay, so that is M1 is mass you have found out 7.13, R is 0.2445, T is again 22 plus 273, that is you get in Kelvin, divided by volume. Volume is 0.34. Okay, now this we will multiply it with 100, so that you will get it in the pressure, you will get it in bar. So the answer is 15.13 bar. So what is the significance of this problem is, in this problem they are given a tank with a certain volume, that is 0.34 meter cube volume, which is a gas, hydrogen sulfide, and the initial temperature, that is T1. Okay, so volume is V. This H2S, you calculate based on that you calculate the molecular weight, that is 2 plus 32, that is 34, and T1 is 22 degrees centigrade, that you add 273, you will get as T1 in Kelvin. Now next is so condition 2, when 2.3 kg of gas is drawn out, then the temperature becomes 15 degrees, so you add again 273 to convert it into Kelvin, and the pressure is 10 bar P2. So what is asked is initial temperature and pressure of the initial mass of the gas and the initial pressure. So very simple thing, we have calculated the molecular weight first, then we have found the gas constant for this particular gas, because we know now universal gas constant, we know R bar, that is 8.3143, that is fixed, and then molecular weight we know. So universal gas constant divided by the molecular weight will give you the gas constant for this particular gas, that is a hydrogen sulfide, that we got as 0.2445. Now for the final condition, mass is equal to PV is equal to MRT. Rearranging, we get M is equal to PV by RT for condition 2. So substituting value P2 into V divided by R into T2, and P, because it is given in bar, we are multiplying with 100 to get it in kilopascals. The mass we get as 4.83, and 4.83 plus that 2.3 kg gas which was taken out, you get the initial mass as 7.13 kg. Now again using the ideal gas relation, PV is equal to MRT, we are finding out P because we know MRT and V. So here again the volume we are dividing by 100, so that you get it in the pressure in bar. Otherwise, if you don't divide, you can write just it in kilopascals. Okay, so this is how you solve a problem. Means you can find out the various, if one unknown is there, you can find out the other things using the ideal gas relationship. P, V, M, R, T is equal to MRT. So there are 5 condition things here. If one is unknown, you can find out by using this relationship, and this relationship you can use for initial condition as well as final conditions, no issues. And only thing you have to remember is, if the pressure is given in bar, you have to multiply it with 100, one thing. Second thing, temperature you have to take in Kelvin only, always, number 2. And the third thing is you have to find out the molecular weight of the substance, and then divide this molecular weight by the universal gas constant to get the R here. This R is not a universal gas constant, this R is for the particular gas, and to find out that gas you should know the molecular weight and then divide the molecular weight by the universal gas constant. This is how you get R. T you get in Kelvin, mass may be given or you calculate. P is in pressure, means in bar, means you multiply with 100, and volume should be in meter cube. This is how you solve the numericals. Thank you. Hello students, now we shall look at the second numerical. A cylinder with a capacity of 2 meter cube contains oxygen gas at a pressure of 4 bar and 30 degrees centigrade initially. Then a leak developed and it was not discovered until the pressure dropped to 2 bar while the temperature remained the same. Assuming ideal gas behavior, determine how much oxygen had leaked out of the cylinder by the time the leak was discovered. So here in this numerical, the volume of the tank is given, that is 2 meter cube. The gas which is stored is given, that is oxygen, and the initial pressure is given as 4 bar and the initial temperature is given as 30 degrees centigrade. Okay, and from that the gas has started leaking. The temperature has not changed, but the pressure has fallen from 4 bar to 2 bar. So assuming ideal gas behavior, we have to find out how much gas, that is oxygen, has leaked out from the cylinder. So using the same relationships like we have seen in problem number 1, that is PV is equal to MRT for initial condition as well as final condition, and as well as you will find out the gas constant, that is R bar divided by M, that is universal gas constant divided by molecular weight. So for oxygen, O2 is 16 into 2, 32, molecular weight is 32. So R is equal to 8.314 divided by 32. We get this as 0.2598 kilojoule per kg Kelvin. We have first found out the R for oxygen. Now, this T1 is given as 30 degrees centigrade. So we'll add 273, it becomes 303 Kelvin. So substituting the values of P1, T1 and V1 in the equation, PV is equal to MRT. Now we have to find out M. So M1 is equal to P1 V1 divided by RT1. P1 is 4 bar, that is 4 into 100, into V1 is 2 meter cube divided by R is 0.2598, we have calculated just now, into T1 is 303 Kelvin. So mass, initial mass 1 is 10.16 kg. Next, after the gas leakage, when the pressure is reduced to 2 bar, so P2 is given as now 2 bar. T1 remains the same, temperature has not changed, so we will take it as 303 Kelvin. Volume also remains same, 2 meter cube. So M2 is equal to P2 V2 divided by RT2. So P is 2 into 100 into 2, that is a meter cube volume, divided by R, that is 0.2598, into 303, that is T2, that you get mass as 5.08 kg. So mass of gas leakage is M2 minus M1, that is 10.16 minus 5.08, that is 5.08 kg of gas has leaked out. So again you can see there are only two things what we calculate here. First is R. We calculate the R of the particular gas. Here it is oxygen. So oxygen is O2. So O2 means 32 we have to take. And R bar is 8.314. This is standard fixed. Second, you have used the same relationship. PV is equal to MRT. We have used for condition 1, that is initial condition 1. And second, we have used P2 V2 by RT2, that is for condition 2 after the leakage of the gas. So if you know this out of this 5, you have to calculate first R, you have to even temperature, you have to bring it in Kelvin, and thus we can solve this problem. I hope you have understood. We will see another 2 problems. Thank you. Hello students, now we shall look at one more problem. Like in a power plant, we use coal for burning, and we have to calculate the amount of air required to burn the coal so that we can have the suitable blowers. Now I will read the question. Air at 1 bar and 25 degrees centigrade is supplied to a furnace of a steam power plant which burns coal at a rate of 2,40,000 kg per hour. If we need 14 kg of air for each kg of coal burned, what should be the volume flow rate of air in meter cube per hour? So this is a question, practical problem of a steam power plant which is using coal as a fuel, and it is burning 2,40,000 kgs of coal per hour, and for each kg of coal it requires 14 kg of air, and this air is supplied at 25 degrees centigrade and 1 bar pressure. Okay, so very simple it is. So volume flow rate of air is V, capital E. Please understand, capital V stands for the volume and small v stands for the specific volume, is meter cube per kg. Volume units are meter cube, whereas small v is specific volume, that is meter cube per kg. So you can see capital V, that is volume of air, is equal to mass of air into specific volume of air. Mass of air is in kg and specific volume is meter cube per kg. So this kg they cancel, and what will remain is meter cube on both left hand side as well as right hand side of the equation. Now what is given for every kg of coal? 14 kg of air is required. So mass of air divided by mass of coal is equal to 14 kg, right? That is given. That is, mass of air is equal to 14 into mass of coal. Therefore, now using these two relationship, volume of air V, air, is equal to 14 into mass of coal into specific volume of air. So this relationship we will use in solving this problem. Okay, but now first we will find out the small v, that is specific volume of air at the furnace inlet. So again, using the ideal gas equation relation, PV is equal to RT here. So this when I am using small v, that is specific volume, M will not come here, okay, because M I had taken in the initial relationship only. So here specific volume of air is equal to RT by P, and now we will find out R. This is a gas constant for now air, and we have to find out the gas constant R from the universal gas constant, that is R bar divided by M. We will find out the R for the air, and the temperature is given at 25. So 25 plus 273 you will get in Kelvin, and P is given as 1 bar, so we will multiply it with 100. So the R bar is 8.3143 divided by air. Air is 28.97. The molecular weight of air is 28.97. If you can't remember this 28.9.7, I can give one more simple way. See, what is air? Air we consider as 80% nitrogen and 20% oxygen, right? That you know, air is 80% nitrogen and 20% oxygen. So what you will do? 80% means 0.8 into nitrogen is N2, that is 28. 0.8 into 28 bracket close, plus 20% is 0.2 into 32. Oxygen is 32. So if you simplify this, you will get as 28.97. Okay. So R is equal to 8.3, that is R bar, that is 8.3143 divided by molecular weight M is for air is 28.97 into T is 273 plus 25 divided by P is 1 bar, that is 1 into 100. So you get the specific volume V of air is 0.855 meter cube per kg. Okay. Therefore, the volume of air required is, now it is given volume of air required is 14 into 2,40,000 kg, that is coal is burnt, and per kg you require 14 kg of air, into the specific volume, that is 0.855. So by solving this, you will get this volume of air required is 2.873 into 10 raised to 6 meter cube per hour. So this is the amount of uh, air required, volume of air required per hour for the steam power plant to burn 2,40,000 kg of coal for, means that is consuming 14 kg of air per kg of coal burnt. So please understand this specific volume we have calculated. Then this specific volume we have calculated using the ideal gas equation, that is PV is equal to RT, and we have found out R of the air here by using molecular weight of R to be 28.97 and P was 1 bar, so we have multiplied by 100. So this is how you solve the numerical. This is a very practical numerical. I hope you please practice this, because this is a very interesting numerical, what I feel. In real life, when you work as engineers, you will be able to calculate this, because this has a very important bearing on the loss of energy also. If you are supplying more air, that is also waste, because the heat is carried away by the excess air. So please solve this numerical, and then we will see one more problem on ideal gas. Thank you. Hello students, now we shall look at one more problem. 5 kg of argon gas undergoes a change of state at constant internal energy. Initial pressure and temperature are 6 atmosphere and 300 Kelvin respectively. The final volume occupied by the gas is 3 times that occupied initially. Assuming ideal gas behavior, determine first the final temperature of the gas and second is the final pressure of the gas. So a very simple and straightforward relation it is. For an ideal gas, the internal energy is a function of temperature only. So if the here it is said that there is a change of state at constant internal energy. Okay. So if internal energy is constant, then the final temperature of the gas is equal to the initial temperature. That is T1 is equal to T2, that is equal to 300 Kelvin. So this answers the first part of the question. The second part is to find out the pressure. Okay, and to find out pressure, again we will use the ideal gas equation, because we are dealing with written that ideal gas behavior should be considered. So P1 V1 is equal to MRT1 and P2 V2 is equal to MRT2. So what happens? T2 is equal to T1. We have seen V1 there is a change, volume is changed. V2 is equal to 3V1. Second number is final volume is 3 times the initial volume. Therefore, substituting these values in these two relationships, because mass of the argon gas is not changing, that is fixed, that is not changed. The R also has not changed. So we are not calculating even the R, because R is same in both the relationships. Only T1 T2 is also same. The right hand side of the relationship equation is same. Therefore, we can, means for initial condition also MRT1 is same, and final condition also MRT2 is also same. Therefore, P2 is equal to P1 divided by 3. Okay. P1 is 6 atmospheric. 6 divided by 3 is 2 atmosphere. P2 final pressure is 2 atmosphere, and you can write it as 2 into 1.01 into 10 raised to 5. That is, you will get it newtons per meter square. So this is a final pressure. So this way, because argon is used as a shielding gas for welding and all. Okay, but because we did not calculate the R in this case, and the 5 kg of argon gas what was given, that is also not required, because the mass is same, whether it in the initial case or final case. only the volume has changed. And the temperature remains same because internal energy is a function of temperature only. So accordingly, what we have done, T2 is equal to T1, that is 300 Kelvin, and we have found out the pressure by using the ideal gas relationship. For initial condition, that is 1, and final condition, that is 2. Okay, thank you.